Hi class. Linear algebra. Today we're going to talk about rank nullity, specifically for Euclidean vector spaces. First, let's figure out our definitions. Definition: the dimension of the null space of A, denoted NA, is called the nullity of A. And recall, as usual, A is going to be an n by n matrix. Real entries. Definition: the dimension of the row space of A, denoted row of A, is the rank of A. Let's talk about how we actually find these things. How to find the rank of A. Step 1, reduce to reduced row echelon form. Step 2, count the non-zero rows. The non-zero rows will form a basis of the row space. And so the rank of A is going to be the number of these non-zero rows, which corresponds to the number of leading variables. Let's do an example. Example: say A is this matrix 1, 2, 4, 2, 1, 3, 4, negative 1, 1. We can row reduce to 1, 0, negative 2, 0, 1, 3, 0, 0, 0. All right. Here's our leading variable 1. It's a leading variable in this row. It's a leading variable in this row. Leading variable is denoted, well, it would be this one and this one, so maybe x and y out of x, y, and z. And so the rank of A is 2. You might have some questions. One question is, why does this work? There's actually a lot of assumptions and things going into that statement above of how to find the rank. So let's talk about the idea of this. What precisely is row reduction? What are our row operations? Our elementary row operations, well, we scale, we exchange 2 rows, we replace a row by its sum with a scalar multiple of another row. And we want to do is to get zeros. We want to get zeros and eliminate vectors. This is why it's sometimes called elimination. I.e., it's a method to show which rows and which row vectors are just basically redundant. Which ones are basically combinations of the other rows. A fact that all of this depends on is that row equivalent matrices have the same row space. We never actually change the underlying vector space, that is the row space. All we're doing is seeing that some vectors representing them are redundant and we can throw them out of our basis. All right, so now we know how to find rank. How do we find nullity? Okay, recall what the null space is. It's all the vectors so that A times that vector is equal to the 0 vector. And so just for notation's sake, let Ri be the ith row of A. All right, so what exactly is A times X? Well, you've got, the first row, the second row, all the way down to the nth row. This is A. And then X is just like so, and we're claiming that this is the 0 vector. All right. Remember how matrix multiplication goes? So we're going to say dot product the first row with this column vector, etc., etc., etc. So what we see is that Ri dot producted with the row vector x transpose, this has to be 0 for all I. Remember what taking the dot product tests. It tests orthogonality. So Ri, this row vector, is orthogonal to x for all I. Let's take a step back and see what this means. The null space of A is the subspace of R to the n that is orthogonal. In the common use of the word orthogonal, we're going to talk about that later. The null space of A is a subspace of Rn that is orthogonal to the row space of A. Let's do an example. Example. Say we've got A is equal to 1, 2, 4, 2, 1, negative 1, 4, 3, 1. All right, we're going to solve this guy. You've seen this matrix before, so I won't bore you with the details, but here's A, and we're going to solve this system. Now we found earlier that, 2, negative 3, 1 is in the null space of A. And in fact, if you're actually going to find the solution to this, you would get alpha times this. Okay. So our null space has dimension 1 with basis 2, negative 3, 1. And you can actually test the orthogonality. Notice that 1, 2, 4, the first row, dotted with 2, negative 3, 1, is 1 by 2, 2 by negative 3, 4 by 1, which is 0. So here's an exercise for you. Exercise. Check that 3, 2, negative 3, 1 is orthogonal to the row space of A by showing that 2, negative 3, 1 is orthogonal to the rows of A. Let's talk a little bit more about this term orthogonality. This is actually a precise thing. And depending on how far we get, we might revisit this many, many times. But definition, two subspaces of Rn, say these subspaces are X and Y, they are orthogonal if X transpose Y is equal to 0 for all X in X and Y in Y. And what we write to denote this is X is orthogonal with this symbol to Y. Definition. Say Y is some subspace of Rn, as before. The orthogonal complement of y is, this is the notation, is defined to be all the vectors in Rn that are orthogonal to all the vectors in Y. Let's do an example. So let's just take our normal setup, nothing fancy. Of our XYZ plane. So if it's our XYZ plane, we know what the unit vector in this direction looks like. This is just I. So the span of I will be, no surprise to anyone, is going to be the x-axis. And we can find two orthogonal vectors. J and K are orthogonal to I. And as you recall, J is going to be in this direction and K is going to be in this direction. The exercise for you is, what is the orthogonal complement? To the subspace span of I. Okay. All of this is to say, if A is an n by n matrix, real entries, the null space of A is the orthogonal complement of the row space of A. And so we can talk about the Euclidean vector space version of the rank-nullity theorem. A is an n by m by n matrix. The rank of A plus the nullity of A is n. How does this help us? We can calculate the nullity by finding the rank. The nullity of A is equal to n minus the rank of A. Here's an exercise for you. Find the nullity of this matrix. Now let's start talking a little bit more about what this means in terms of dimension. Let's talk about lemma 26. Say A and B are row equivalent matrices. A times C is equal to 0, C the vector, column vector, if and only if B times C is equal to 0. Row equivalent matrices have the same null space. Let's prove this. Proof. Say A is row equivalent to B. This means, of course, as usual, there exist elementary matrices, E1 through En, that represent the elementary row operations that takes us from one matrix to another. E1 through En times A is going to be equal to B. So if AC is equal to the 0 vector, this means that E1 through En times AC is also equal to the 0 vector. But of course, this is just B. So BC is equal to the 0 vector. We can do the same argument again but in the other direction, vice versa, since A is going to be equal to En inverse E1 inverse B, where those two are elementary matrices. End of proof, QED. The reason that we want this lemma is to prove the next theorem. Theorem 27. If A is an m by n matrix, then the dimension of the row space of A, we claim, is equal to the dimension of the column space of A. This is a little bit complicated, so I'm going to include the idea and examples of each step as we go along. Here's the proof. So we're just going to say that R stands for the rank of A, just to keep things short. We're also going to say that U is the reduced row echelon form of A. Every matrix has a reduced row echelon form. So say we've got 1, 2, 4, 2, 1, 3, 4, negative 1, 1. We're going to reduce to get 1, 0, negative 2, 0, 1, 3, 0, 0, 0. So this would be A and this would be U in this argument. And the rank, as we talked about before, of A would be 2. The next step of our proof is to erase all the columns in U corresponding to free variables. And the result is going to be UL. So this column corresponds to a free variable. We're going to erase that. And so UL is going to be the matrix 1, 0, 0, 0, 1, 0. I'd just like to point out here that the number of columns is going to be the number of variables that we didn't erase. Something that's not a free variable is going to be a leading variable. So the number of columns left is the number of leading variables, which is precisely the rank. In this case, that's 2. Next step, we're going to erase the corresponding columns in A. So if we started out with A is equal to 1, 2, 4, 2, 1, 3, 4, negative 1, 1, we are erasing the same column that we erased for U, and we're going to get, the result is AL. We're going to get AL is equal to 1, 2, 4, 2, 1, 3. Okay. Remember that U and A were row equivalent. We just threw out a column, so UL and AL will also be row equivalent. So because UL and AL are row equivalent, UL is equal to UL times C is equal to the 0 vector if and only if AC is equal to the 0 vector by lemma 26. So here's what that means. Notice the columns in UL are, by design, linearly independent. This means that UL times C is equal to 0 has only the trivial solution. If you're going to combine the columns of U and get 0, you're going to only have the trivial solution. This means that AL times the same C is equal to 0 has only the trivial solution. Oh, there's only one possible value for C, 0. And this means that the columns of AL are linearly independent. Okay, so let's talk about what we have. The dimension of the column space of A. It's going to be greater than or equal to the dimension of the column space of AL, because we threw out a column to get AL. The dimension of the column space of AL is equal to the dimension of the column space of UL, and we already know that that's R, where R, remember, was the rank of A to begin with. Okay, so we've shown that the dimension of the column space of A is greater than or equal to R, which is the rank of A, which is defined to be the dimension of the row space of A. Okay, let's prove the other inequality. What we know is that the dimension of the row space of A is going to be equal to the dimension of the column space of A transpose. The rows of A become the columns of A transpose. The column space of a matrix is going to be greater than or the dimension of the column space of a matrix is greater than or equal to the dimension of the row space of that matrix. We've already proved that just above. So this is going to be greater than or equal to the dimension of the row space of A transpose. But the row space of A transpose is the column space of A. So this is the dimension of the column space of A. So we've shown that the dimension of the column space of A is less than or equal to the dimension of the row space of A. And we've also shown the other inequality. So the dimension of the row space of A is equal to the dimension of the column space of A. While the row space of a matrix and the column space of a matrix are certainly usually different vector spaces, they will have the same dimension. QED, end of proof. Let's stop there, but I do want to acknowledge some questions that you might have. Here is a question that I have. We did rank nullity for Euclidean vector spaces, but we know that there are vector spaces that aren't Euclidean vector spaces. The polynomials, continuous functions, etc., etc., etc. So is there an idea of rank and nullity in vector spaces other than the Euclidean vector space? Of course, we will have to have an idea of rank and an idea of nullity to begin with. There is a way to translate this to other vector spaces. We'll get to that later. For now, think on this. Talk to you next time.